It's section 12.4, support vector machine. So far, you learned about perceptron add-line and logistic regression. Those algorithms would stop or slow down the convergence when the linear separator becomes one of the hyperplanes shown in this figure. For example, the perceptron will completely stop when reaching at one of these hyperplanes. Assume we have this hyperplane and a new point is given around here, then apparently this must belong to that side. However, the algorithm will predict this point for as one of these points. So it is erroneous. Even though the separator is made perfectly for given training data set, it can be erroneous. The question is, how can we get really good, reliable hyperplane? That's the idea of supported vector machine. Look at this figure, right side, and we'll try to find the separator as in this dashed line so that the strip margin is as large as possible. So we try to maximize the margin. That's the idea of supported vector machine. Okay. Supported vector machine is developed in 1995, and the key idea is maximizing the margin. The rationale behind having decision boundaries with large margins is that they tend to have a lower generalization error, and whereas models with small margins are more prone to overfitting. Let's see the derivation for the supported vector machine. Now, we get the weight so that, and that input, the equation is 0, and that is 1, and this is a -1. And then we try to maximize the margin. So start with the equations for line, and that is now the net input is 1, and this is a net input is -1. Okay? And in this way, we start with the positive and negative hyperplanes, and from positive side points, the value is 1, and this is a boundary. And also for negative points, this boundary is a -1. The value is a -1. Now from this one, we can get that equation, just subtract, then we reach this equation. Now divided by the W norm, then here we have this equation. Now we have to understand this equation. Okay, that is dot product. Dot product is a kind of a projection. So let's go back to the figure. Okay, for example, now is x plus minus x minus. That one will be this vector. And W for these lines, W is a normal vector. Now W and over is norm length. That is unit vector in that direction, the normal direction of the hyperplanes. So that now we have normal vector in that direction, and this one is projected onto this line. So eventually x plus minus x minus, and along with the dot product here, then that is exactly from here to there. Length of that one, okay. So it's projected to the normal direction. Okay. So this left-hand side is, in fact, the margin. Okay, that's the margin. And so we have to maximize this one, but it is the same as that. So its reciprocal must be minimized. Here we have the mathematical formula for the supported vector machine. So we will try to minimize this norm squared. Once this one is minimized, then as norm squared is also, its square must be minimized there, so that the minimizing, if maximizing this quantity is the same as minimizing its reciprocal, and also same as minimizing norm squared. So we have a formula here. So in supported vector machine, we have to minimize and half W norm squared, and subject to these conditions are satisfied. Okay, for positive points on the boundary, the value is 1, but for other positive points, it can be larger than 1. Also, along with the same logic, on the boundary of negative points, the value is -1, but for other points, it can be less than -1. Okay, so that is the formula, and we have to solve this problem. And of course, for these two inequalities, we can write them in this way. We multiply the labels. Here, we choose just 1 and -1. And in the case, if you multiply the labels, then you can write in this way for every point. And quite easily you can check that these conditions are the same as this one. Okay. Okay. So we have to solve the constrained optimization problem, and we can use the method of Lagrange multipliers. You learned already this technique. Now here we recall the linear supported vector machine in this way. Then it's a Lagrangian, can be formulated in this way. Now this is original object function, and along with Lagrange multipliers, it's dual variables, and now this component and multiplication, and for every point I, and you get that one, and summation. That is now the Lagrangian. Okay, we have to solve this problem, and by using some theory from the optimization problems, we can see that now original problem is minimizing over the original object function. Now along with the Lagrangian, now the problem becomes minimax problem. But this minimax problem is equivalent to the original problem. So we say this is the primal problem. And once you change the order of this minimization and maximization, then it becomes dual problem. We call this problem the Lagrange dual problem or dual problem. But sometimes we say max-min problem. Now this is a dual problem for quadratic problems. And this dual problem is equivalent to the original primal problem. So here we have now quadratic problem. Look at over there. The objective function is quadratic and the constraints are linear inequalities. So it is a kind of a quadratic problem. Now, when we deal with this quadratic problem, then dual formulation is quite effective and always produce the same solution. Okay. Now we focus on this portion first. Then here derivative, once this whole thing is found, and so that we assume optimal values for W side and dual variable side and found, then at the points, and here the derivative with respect to W and W0 and evaluated at the optimal points must be 0. It is a necessary condition. So gradient W of the Lagrangian evaluated at the optimal points must be 0, and also W0 derivative at the optimal values must be 0. Okay, start with this one. We can collect some conditions for now the necessary conditions. Then we can get so-called KKT conditions. In optimization, KKT conditions are first derivative test and also first order necessary condition for solution of nonlinear programming to be optimized. Let's see the whole set of KKT conditions. Okay, W derivative, the gradient, can be found in this way, must be 0, which implies W as this one. So we can find the relation between W and X. In fact, W and alpha, the Lagrange multipliers, and also W0 derivative becomes this one, equals 0, so we reach this equation. Now the Lagrange multipliers must be non-negative. That is called dual feasibility. We'll try to solve the problem along with the Lagrange multipliers non-negative. And that is the primal feasibility. This is original constraint conditions. Now, mathematically, we can prove this one. Here, Lagrange multipliers and the primal feasibility. If you make multiplication, this product must be always 0. So one is loose, which means that is positive, then the other must be 0. And if it is loose, then it must be 0. So it is called complementary slangness. Okay, along with these equations, we can solve the dual problem. Now, for the Lagrangian, okay, that is the expansion, and it's the same. We didn't do anything for the Lagrangian. This Lagrangian, okay, here, can be written that way. Here we multiply and spread out. So that is exactly this one. Now, from the KKT conditions, we know that is now, this is just simply W0 is multiplied for that term, so it must be 0. Now here, that is, okay, WT, so it's a dot product along with this limited term, which must be again W. So that this term must be same as W transpose W. So it's a W norm squared, and we have another term over there. So this will be the same as that one by using these KKT conditions. Okay, from these two, we have negative W norm squared and alpha I. Now again, we can eliminate W norm squared by using that condition, W norm squared. Then now here, minus half W norm squared is minus half W and W. And we can write in this way. So this portion can be replaced by this one, and we end up with this one. So here, now the dual problem can be formulated in this way. Now this one is concave. Now this is a linear term for the Lagrange multipliers, and this is quadratic along with negative, so that it is a concave problem. So solving this problem is much easier than original problem. And of course, along with these conditions, each Lagrange multiplier must be non-negative, and this one must be satisfied. Along with this constraint, this problem can be solved not so difficult by using, for example, some quadratic programming technique or well-known sequential minimal optimization, SMO. You can solve this problem. We will not go to the detail of the solution of this dual problem. Now we'll assume we found optimal value for this problem. So alpha star is now the collection of Lagrange multipliers in optimum. Okay, then by using these optimal values for Lagrange multipliers, and by using the first KKT condition, we can obtain W star. Let's go back to the conditions. Once we know alpha values, and already this is given data point and label, so that once alpha values are known, then we can decide the W. And also by using these equations, we can decide also W0. Okay, so once we found alpha value, optimal values, then we can decide W optimum quite easily. And now here we consider the complementary slackness KKT conditions, this equation. That means that alpha I star is positive, then the other side must be 0, so it must be 1. And once it's negative, it cannot happen, because when we solve the problem, always we try to get alpha I star non-negative. It's impossible. Now, once it is loose, it's positive, then the Lagrange multiplier must be 0 to satisfy this equation. And also it cannot happen. So we can have this one or this one. Now we define the optimal scoring function, and that is net input score function. Now alpha I is positive, then the value must be along with, for example here, along with this one, so that must be 1. Now we'll use this equation to find the W0 star. Okay, so here, now to get W0 in optimal value, use the primal feasibility condition in that one. So that minimum of that will be 1. So we multiply and move this one to the other side. Then now we have, only we are choosing y equals 1, then we ignore this portion and move this one along with the minimum, which is this one. So we can decide W0 in optimum. And so we done. We found the first, the Lagrange multiplier, and then we can decide W star and W0 star. Okay. Now here, so that anyway, and eventually, okay, look at over there. This complementary slang is saying that now alpha I is positive, that is tight. So that means that, okay, once we try to make the strip and maximum margin, so that on the boundary, and alpha I is positive point on the boundary. However, once go over there, then it's now this value is positive, so that alpha I and for other point must be 0. So that now only point on the boundary will make the alpha value positive. So that in a sense, these are in the vectors on the boundary are supporting vector for the values of alpha I, Lagrange multipliers. So that, and we call this point the support vectors. So the name of the algorithm is made support vector machine. Okay. Okay, that's the end of the first part, and we'll continue in the second subsection. Thank you.